Hello, and welcome back to the Sleepy Geographer. Tonight we're traveling to one of the strangest stretches of ground found anywhere on the surface of the Earth. A place that sits below sea level, sits astride three pieces of the planet's crust as they slowly pull apart from one another, and holds within its boundaries a lake of open, glowing rock, fields of mineral color unlike almost anywhere else on the continent, and some of the hottest average temperatures ever recorded for a place where people actually live. The Danakil Depression. Before we begin, let me know in the comments where you're listening from and what time it is for you. I always enjoy seeing people from so many different corners of the world joining these peaceful journeys. Now, get comfortable, settle in, and let's begin. Picture standing at the edge of a plain that stretches out flat and pale in every direction, the ground beneath your feet crusted white in some places, crumbling into fine, colored powder in others. Ahead of you, patches of green and yellow and burnt orange spread across the earth in shapes too irregular to have been made by anything other than slow, patient chemistry working itself out over years, decades, centuries. The air shimmers even in the shade. Somewhere in the distance, a low ridge of dark volcanic rock breaks the flatness of the horizon, and if you were to walk toward it long enough, you would eventually find something almost nowhere else on this planet allows you to find so easily. A lake of molten rock, open to the sky, glowing faintly red even in full daylight. This is northeastern Ethiopia, close to the borders with Eritrea and Djibouti, in a region often referred to more broadly as the Afar Triangle. It's a remote stretch of land, reached today mainly by rough tracks crossing open desert, accessible to outside visitors only with considerable logistical planning and, in most cases, local guides familiar with a terrain that offers few landmarks and even fewer sources of water along the way. There are no paved roads reaching most of the interior of this landscape. There is no shade to speak of, beyond whatever shadow a traveler's own vehicle or body happens to cast. And there is very little, across long stretches of the journey inward, to mark distance or direction at all, beyond the position of the sun overhead and the particular knowledge carried by guides who have spent their whole lives learning to read a landscape that offers almost nothing in the way of conventional signposts. Researchers who study the origins of life and the possibility of life on other planets have spent years working in this exact landscape because so little about it resembles anywhere else they could otherwise study. Some have described their first arrival here after the long drive in across open desert as feeling less like reaching a remote corner of Ethiopia and more like stepping onto ground that shouldn't, by any ordinary logic, exist on this planet at all. Somewhere within one of the acid pools scattered across this landscape, a single mineral crystal is beginning to form tonight, drawn slowly out of water saturated with dissolved salts and minerals far beyond what almost any other environment on the planet could sustain. It begins as almost nothing, a faint irregularity in the water's chemistry, a handful of atoms finding each other and beginning, patiently, to arrange themselves into the ordered lattice that will eventually become something visible, something with edges and faces catching whatever light reaches down into the pool's shallow water. This crystal will return throughout tonight's journey, its slow growth marking the passage of the hours we spend here, and eventually the wind will lift it and carry it out across the wider salt plain surrounding the pool where it formed. Its story, small and easily overlooked, mirrors the Depression's story as a whole, something built patiently from forces most of us never think to consider in a place shaped by conditions found almost nowhere else. What makes this depression worth traveling toward, despite the difficulty of reaching it, begins with something straightforward to state but genuinely difficult to picture. Much of this land sits below sea level. Parts of the depression drop to more than 100 meters below the level of the ocean, making this one of the lowest points on the entire African continent and among the lowest exposed land surfaces found anywhere on Earth that isn't currently covered by water. This is worth stating carefully, because lowest point on land is a claim that shifts depending on exactly how it's measured and which specific location within the depression is being discussed. Different points across this uneven basin sit at different elevations, some considerably lower than others, and the deepest confirmed sections rank among a small handful of places on the planet's surface that share this particular distinction of sitting so far below the ocean's own level while remaining, technically, dry land. It's worth pausing on what below sea level actually means when standing on ground this flat and this dry, because the phrase can be misleading if pictured too literally. There is no ocean visible anywhere nearby, no obvious sign that this ground sits lower than the distant, invisible surface of the sea. The nearest coastline lies many kilometers away, across the Red Sea and the Gulf of Aden. What below sea level means here is a measurement, a comparison drawn against a reference point most visitors will never actually see, and yet the consequences of that measurement are entirely real, shaping temperature, air pressure, and the movement of what little water does exist across this landscape. Being this low matters more than it might initially seem, because elevation shapes climate in ways that compound rather than simply add together. Lower elevation generally means hotter conditions, all else being equal, since there's less atmosphere above a given point to allow heat to escape efficiently into space. The air itself, at this depth below sea level, is denser than it would be at higher elevation, and that density plays its own quiet role in how heat behaves here, how it gathers close to the ground rather than dispersing upward the way it might in thinner air higher up a mountainside. Combine that basic relationship between elevation and heat with the depression's position close to the equator, and with a landscape almost entirely stripped of vegetation, capable of providing shade or releasing cooling moisture into the air, and a picture begins to form of why this particular stretch of ground has developed a reputation as one of the hottest inhabited environments on the planet. That reputation deserves its own careful treatment, separate from the discussion of elevation, because temperature and elevation, while related, are not the same measurement, and conflating them risks producing exactly the kind of unqualified superlative worth avoiding. Long-term average temperatures recorded in parts of the Danakil Depression, particularly around settlements like Dalol, have ranked among the highest annual averages ever documented for any inhabited location on Earth, with some historical records placing the yearly average well above 30 degrees Celsius, a figure that accounts for cooler nighttime hours as well as the extreme daytime heat, meaning the actual midday temperatures across much of the year climb dramatically higher still. Different studies and different measurement periods have produced somewhat different specific figures, and comparing this depression against other extremely hot regions of the world involves genuine scientific debate about methodology, the length of record available, and which specific metric, average annual temperature, average daily maximum, or absolute recorded peak, best captures what hottest actually means. What can be said with confidence, without needing to settle every detail of that debate, is that this depression sits consistently among the very small number of places on Earth where human settlements exist at all, despite conditions this extreme, and that the heat here is not an occasional, seasonal event, but something closer to a permanent, year-round condition shaping every aspect of life within the depression's boundaries. Picture what this actually means for the ground itself, hour by hour, through an ordinary day. In the earliest hours before sunrise, the landscape holds something close to relief, the ground having released much of the previous day's stored heat into the clear night sky above it, the air carrying a temperature that, while still warm by most standards elsewhere in the world, feels almost gentle compared to what will follow once the sun climbs higher. By mid-morning, though, the pale salt and mineral-crusted earth has already begun radiating heat back upward, the air above it visibly distorting, bending light in shimmering waves that make distant features of the landscape appear to float and ripple rather than sit still. By early afternoon, the heat has become something closer to a physical presence than simply a measurement on a thermometer, pressing down from above and rising up from below simultaneously, leaving almost no comfortable direction to turn. Shadows, where they exist at all, offer only a partial reprieve, since even shaded ground here often remains hot enough to make direct contact uncomfortable. And through it all, the sky above typically remains almost entirely clear, offering no cloud cover to interrupt the sun's direct path toward the ground below day after day across a year that offers remarkably little seasonal variation compared to almost anywhere else people manage to live permanently. Rainfall across this depression is correspondingly slight, arriving rarely and unpredictably in quantities so small across an average year that the region qualifies among the driest inhabited environments found anywhere on the continent. What little moisture the landscape does receive tends to evaporate quickly, drawn back into the dry air almost as soon as it touches the superheated ground, leaving behind only the faintest trace of its passage, a slightly darker patch of soil, gone again within hours, sometimes within minutes. Occasionally, a distant storm somewhere in the surrounding highlands will send a brief pulse of water down through one of the dry channels crossing the depression's floor, a rare and sudden event locals recognize immediately by the particular smell it carries: wet stone and disturbed dust rising into air that has forgotten, across the previous months, what moisture even smells like. And yet, despite all of this, people do live here. Communities have made their homes within and around the edges of this depression for generations, developing an intimate, practical understanding of exactly how to survive in conditions that would overwhelm most visitors within a matter of days. Their particular relationship with this landscape, the salt they cut from its floor and the routes they've walked across it for as long as anyone can remember, will come into this story more fully a little later tonight, once we've explored more of the terrain that has shaped their way of life so directly. For now, the question worth sitting with is a different one entirely. Given how extreme this landscape's conditions are, how low its elevation runs, how relentless its heat remains across the calendar year, the deeper puzzle isn't simply how anyone survives here. It's how a landscape like this came to exist at all. Why does the ground here sit so far below sea level in the first place? Why is this particular stretch of Ethiopia shaped so differently from the plateaus and highlands surrounding it on almost every side? Some of them rising more than 2,000 meters higher than the depression's own lowest points, within a distance that, on a map, looks almost too short to account for a difference in elevation so dramatic. The answer lies underground, in a process that has been unfolding, slowly and continuously, for millions of years, and that is, even now, actively reshaping the deep structure of this part of the African continent. Beneath the visible surface of the Danakil Depression, in the deep rock forming the foundation of this entire region, three of the Earth's major tectonic plates meet at a single point, a location geologists refer to as a triple junction. This isn't a meeting in the sense of three plates simply touching one another and holding still. It's a meeting in the sense of three plates actively pulling apart from one another, each moving in a slightly different direction, stretching the crust between them thinner and thinner across a stretch of time reaching back several million years and continuing, without pause, into the present moment. To understand why this matters so directly to the shape of the depression sitting above it, it helps to picture, briefly, what the surface of the Earth actually is at this kind of scale. The planet's outer shell isn't a single, continuous piece of rock, but rather a collection of separate plates, some carrying entire continents on their surface, others carrying ocean floor, all of them moving slowly across the more fluid layer of rock beneath them, driven by heat rising from deep within the planet's interior. Most of the time, this movement happens at a pace far too slow for anyone to notice directly, measured in centimeters per year, a rate close to the speed at which human fingernails grow. But across sufficient time, movement at even this modest pace accumulates into changes on a genuinely dramatic scale, splitting continents apart, building mountain ranges, opening entirely new ocean basins where none existed before. The Danakil Depression sits directly above one such site of active splitting, where the African plate is gradually dividing into two separate pieces, commonly referred to by geologists as the Nubian plate to the west and the Somali plate to the east, while a third plate, the Arabian plate, pulls away toward the northeast, having already separated more fully from Africa to form the Red Sea. All three of these plates meet and interact in the region around the Afar triangle, each one tugging in a slightly different direction, and the depression itself sits close to the heart of where that three-way stretching is currently concentrated most intensely. Picture the crust in this region the way you might picture a sheet of material being pulled slowly apart from three different directions at once, thinning gradually at the point where all three pulls converge. As the crust here stretches, it doesn't simply tear apart cleanly and immediately. Instead, it thins gradually, sagging downward as it does, the same way a piece of dough stretched thin between two hands will droop and thin in the middle before any actual tear appears. This gradual thinning and sagging is precisely what has produced the depression's unusually low elevation, ground that would, under ordinary circumstances, sit at or above sea level like the rest of the surrounding region, instead dropping well below it as the crust beneath continues its slow process of separation. This stretching hasn't happened and isn't happening evenly across the entire region. Some sections of the depression have sagged further than others, creating the uneven, basin-like terrain that gives the wider landscape its particular, irregular character, low points scattered unevenly across the depression's floor rather than forming one single, uniform surface. Certain areas continue actively sinking even now, at rates that, while far too slow to notice within the span of an ordinary human visit, have been measured and tracked by researchers using precise satellite instruments capable of detecting ground movement on the scale of mere millimeters per year. Cracks appear periodically along the surface in certain zones, some opening gradually over months, others appearing suddenly during periods of heightened underground activity, visible evidence of a process that, across the length of a single human lifetime, remains almost entirely invisible, and yet across the scale of geological time is doing nothing less than slowly tearing a continent apart. The volcanic activity scattered throughout this landscape is directly connected to this same process of stretching and thinning. As the crust here grows thinner, it becomes easier for molten rock rising from deep within the Earth's mantle to reach the surface, finding paths upward through fractures and weaknesses created by the ongoing separation of the plates above. This is part of why the Danakil Depression holds not only unusually low elevation and unusually extreme heat, but also some of the most direct, visible volcanic activity found anywhere on the continent. Magma rising close enough to the surface in certain specific locations to be seen glowing openly, rather than remaining hidden beneath layers of solid rock the way it does across most of the rest of the world. There is something worth pausing on here in the deep, ongoing nature of this process. The forces reshaping this landscape aren't the remnant of some ancient, long-finished chapter of the planet's history, the way the geological forces shaping many other famous landscapes elsewhere in the world often are. They are active, continuous, and ongoing, still working, right now, exactly as they've worked for millions of years already. Geologists studying this region have concluded that the stretching happening here represents an early stage in a much longer process, one that, If it continues across the scale of time, geological processes typically require will eventually split this portion of Africa apart entirely, allowing ocean water to flood into the depression and connect it permanently to the Red Sea, creating, over a length of time reaching millions of years into the future, an entirely new ocean basin where dry, superheated desert currently sits. It's a strange thing to stand on ground this dry, this cracked, this thoroughly hostile to water in almost every form, and understand that it is, in the slowest and most patient sense imaginable, in the process of becoming seafloor. Nothing about the landscape as it exists today offers any visible hint of that future. The salt crusting the ground here formed, in fact, from the evaporation of ancient seawater that once did flood this basin, long before the depression sank to its current depth, water that arrived, stayed for a time, and then departed again as the climate shifted and the connection to the sea closed once more. What the deep, ongoing stretching of the crust promises now is a return to that condition. Not a repeat of the past exactly, but a continuation of the same fundamental process, land sinking, seawater eventually finding its way back in, only this time with no clear reason to expect the connection will ever close again. The idea of an ocean still being born beneath this dry, cracked ground is one this story will sit with more fully later tonight. Once more of the landscape this ongoing process has already produced has been properly explored. For now, it's worth simply holding the image quietly in mind, that beneath the flat, mineral-crusted ground of the Danakil Depression, beneath the acid pools and salt flats and volcanic ridges waiting ahead in this journey, three pieces of the planet's crust continue pulling steadily apart from one another, exactly as they have for millions of years, patiently, persistently reshaping the deep architecture of this stretch of Africa long after any single human visitor to this landscape has come and gone. That same stretching and thinning, that same rising of material from deep within the earth is responsible for something else entirely, something visible immediately to anyone standing at the surface rather than requiring instruments capable of measuring millimeters of movement across a satellite's view. It is responsible for color, for a landscape that looks, in certain stretches, almost impossible to have occurred through natural processes alone, ground stained in shades of green and yellow and burnt orange that few other places on the planet's surface ever produce. The particular chemistry rising up through the same cracks and fissures created by the pulling apart of the crust beneath has, over a long stretch of time, built that landscape mineral by mineral, layer by layer, across the surface of one of the strangest stretches of ground found anywhere on Earth. Somewhere within it, sulfur gathers in bright yellow crusts along the edges of pools too acidic for almost anything to survive within them directly. Iron oxidizes into deep rust reds where groundwater meets air after rising from far below. Salts of every kind crystallize into pale greens and chalky whites, spreading in slow, uneven patterns across ground that looks, from above, closer to something painted than something grown from rock and heat and water alone. Steam rises in thin, wavering columns from certain vents scattered across this ground, carrying with it a faint mineral sharpness in the air, noticeable even from a distance, a reminder that everything visible on the surface here is connected, directly and continuously, to processes unfolding in the hot rock not very far beneath it. Walking closer toward one of these colored fields, the ground itself begins to change character with almost every step, hardening in some places into something close to a crust of glass, crumbling in others into a soft, granular powder that shifts and settles underfoot in a way that feels closer to walking across old snow than across desert ground. Pools of liquid appear scattered among the color, some barely larger than a footprint, others spreading wide enough to reflect the sky above them, their surfaces sometimes still and glassy, sometimes gently disturbed by rising gas bubbles breaking the surface tension one at a time, each release accompanied by the faintest sound, a soft, wet pop lost almost instantly into the wider silence surrounding it. That colour and the pools producing it form a stretch of ground where the ordinary rules of what a landscape is supposed to look like no longer seem to apply. There is a particular quality to the light in this part of the depression that visitors often mention long after they've left. A brightness that feels different from ordinary desert sun, sharpened somehow by its reflection off the pale salt and the flat, mineral-crusted ground stretching away in every direction. At certain hours, especially in the earlier part of the day, that light catches the surface of the coloured pools at exactly the angle needed to make the water itself seem to glow faintly from within, the greens and yellows deepening for a short while before the sun climbs higher and the effect fades into something flatter, more ordinary, until the cycle begins again with the following dawn. Sound behaves strangely here too, in a landscape offering so little in the way of vegetation or structure to absorb or redirect it. A voice carries much further across this open, hard ground than it would across softer terrain elsewhere, and the low hiss of steam escaping from some distant vent can sometimes be heard from a surprising distance, carried across the stillness with a clarity that makes the source feel closer than it actually is. Wind, when it moves across this landscape, does so almost without obstruction, gathering loose grains of salt and mineral dust and lifting them into low, drifting curtains that catch the light and then settle again just as quickly, leaving no permanent trace once they've passed. It's worth remembering, standing amid all of this colour and heat and strangeness, that every single feature scattered across this landscape traces back to the same underlying cause, the same slow pulling apart of the crust described a little earlier in this journey. The colours exist because the thinning crust allows mineral-rich water and gas to rise toward the surface. The heat exists because the depression sits low enough and close enough to molten rock rising from below, that ordinary desert warmth compounds into something considerably more extreme. Even the flatness of the ground itself, the wide, level plains stretching out toward every horizon, exists because this basin has spent long stretches of its history filled with water, evaporating and refilling across cycles reaching back much further than any human record could properly trace, each cycle leaving behind another thin layer of mineral sediment, smoothing the terrain further with every repetition. Nothing about this place happened by accident, and nothing about it happened quickly. Every colour, every pool, every drifting curtain of wind-carried salt represents the visible surface of a process that has been running, patiently and without pause, for a length of time this journey has only begun to properly measure. Closer to the ground, the colours separate themselves into individual textures, each one telling its own small story about the particular chemistry rising up from below at that exact spot. In one place, a crust of pure sulfur has formed thick enough to crunch faintly underfoot, its yellow so saturated it looks less like a mineral deposit and more like something spilled deliberately across the rock, still wet in appearance even where it has long since hardened solid. A few steps further, the ground shifts to a pale, sickly green, the colour produced by a particular combination of dissolved iron and other trace metals interacting with the acidic water seeping up through cracks in the surface. Further still, patches of deep rust orange spread in wide, uneven stains, iron oxidizing on contact with air after arriving from far below in a form the rock had kept hidden from oxygen for a very long time before this moment. None of these colours were placed here by anything resembling intention. They are the visible result of chemistry working itself out according to rules as old as the elements involved. Sulfur reacting with sulfur, iron reacting with oxygen, salts crystallizing out of water as it evaporates and leaves behind whatever it once carried in solution. And yet the effect, walking through it, is difficult to shake free of the sense that some deliberate hand shaped this ground, laid out in patches and streaks, too organized looking to have arisen from anything as simple as water rising, evaporating, and leaving its dissolved minerals behind. Geologists who study this particular field closely have mapped its coloration against the underlying chemistry with considerable precision, tracing each patch of green or yellow or orange back to the exact combination of minerals responsible, the temperature of the water that deposited it, and the rate at which that water evaporated once it reached the surface. Faster evaporation tends to produce sharper, more concentrated bands of color, the dissolved minerals crystallizing out quickly before they have much chance to spread or blend with neighboring deposits. Slower evaporation allows more gradual mixing, softer transitions between one color and the next, the boundary between a patch of yellow sulfur and a patch of green iron-stained ground blurring into a transitional zone rather than presenting the sharp edge visible where evaporation happened more rapidly. The pools scattered across this stretch of ground deserve their own close attention, because they are, in their own quiet way, some of the most hostile bodies of liquid found anywhere on the planet's surface, and also, paradoxically, host to some of the most resilient forms of life scientists have ever documented. The water filling these pools arrives from deep underground, heated by the same volcanic processes responsible for the region's extreme surface temperatures, and carrying with it a concentration of dissolved minerals and acids that would make the water almost instantly harmful to most living things that might otherwise attempt to drink from it. Some of these pools register acidity levels closer to battery acid than to anything typically described as water in ordinary conversation. Their pH low enough that a hand dipped into certain pools would come away burned within moments. Temperature varies considerably from one pool to the next, some barely above the surrounding air temperature, others hot enough to make close approach genuinely dangerous. The water itself sometimes visibly disturbed by heat rising directly from a vent connected to deeper, hotter reservoirs below. Local guides who lead visitors through this terrain have learned, through long experience passed down across generations, precisely which pools are safe to approach closely and which demand a wide, cautious berth, knowledge that exists nowhere in written form, carried instead entirely within the memory of people who have spent their whole lives moving carefully through this landscape. And yet color persists across nearly all of them. Greens and yellows and occasional deep reds, shifting subtly depending on the particular mineral balance of that specific pool, the temperature of the water rising from below, and the concentration of whatever microscopic life has managed to establish itself within conditions this extreme. We'll spend considerably more time with that microscopic life later in this journey, because what survives here, thriving in water most of the planet's organisms would find instantly lethal, has become one of the most significant reasons researchers keep returning to this particular landscape decade after decade. For now, it's worth simply absorbing the scene as it presents itself at ground level. Shallow, brightly coloured pools scattered across an otherwise pale and cracked landscape, steam rising here and there where the underlying heat pushes closest to the surface, the whole scene shifting subtly in colour and texture depending on the angle of the sun and the particular hour of the day. Early morning light tends to soften the colours, giving the whole landscape a slightly muted, watercolour quality before the sun climbs high enough to sharpen every edge and intensify every hue. By midday, the colours reach their most vivid expression, the greens deepening, the yellows brightening almost to the point of looking artificial, the whole scene taking on an intensity that feels almost too saturated to have occurred without some kind of deliberate enhancement. The salt crusts bordering these coloured pools carry their own particular texture, brittle in some places, soft and yielding in others, shaped into small ridges and hollows by the slow accumulation and evaporation of mineral-laden water across countless previous cycles. Walking across these crusts produces a sound unlike walking across almost any other surface, a light, crackling crunch, occasionally interrupted by a hollow, resonant note where the crust has formed a thin shell over a small pocket of trapped air or liquid beneath. In certain places, the ground gives slightly underfoot in a way that raises an instinctive caution, a reminder that not everything about this landscape's solid appearance can be entirely trusted, that beneath the pale, crusted surface, water and heat continue moving in ways not always visible from above. Some of these formations rise into small, irregular towers and mounds, built up gradually as mineral-rich water seeps out through a particular vent or crack and evaporates almost immediately upon reaching the air, leaving behind another thin deposit of salt and sulfur with each new pulse of liquid. Over years, these deposits accumulate into shapes that seem, at a glance, almost architectural, rounded columns and low domes scattered across the ground like the remains of some structure built and then abandoned, though nothing here was ever built in any deliberate sense at all. Each shape is simply the visible record of water finding a particular path to the surface and repeating that same path over and over, the mineral content of each evaporation cycle adding one more thin layer to whatever had already accumulated before it. Some of these small towers have grown tall enough to cast their own shadows by mid-morning, brief pools of shade quickly claimed by whatever insects manage to survive in this otherwise unforgiving terrain. Certain sections of this mineral field carry a faint but distinct smell, sulfur mixing with the sharper, mineral scent of the hot springs feeding the pools. An odor most visitors describe as unpleasant at first encounter, but oddly unmemorable within a short time, the senses adjusting quickly to a smell this landscape treats as entirely ordinary. Small gas vents scattered among the pools release a continuous, faint hiss, bubbles rising and breaking the surface of certain pools in a slow, irregular rhythm, each release a small reminder of the pressure building somewhere beneath the ground, seeking whatever path upward happens to be available at that particular point. Watching one of these vents for long enough, the rhythm begins to feel almost conversational. A pause, a release, another pause. The ground itself seeming to breathe in a pattern too slow and too irregular for any human observer to predict with real confidence. It's within exactly this kind of environment, water this acidic, minerals this concentrated, that the mineral crystal introduced earlier in this journey continues its own slow formation tonight. Deep within one particular pool, dissolved salts continue gathering around whatever tiny irregularity first gave them something to cling to, layer accumulating upon layer in the same patient, wordless process responsible for every crystal that has ever formed anywhere on this planet. Its growth is invisible at any single moment, undetectable across the span of a single observation, and yet entirely real, continuing steadily whether or not anyone happens to be standing nearby to notice it. The particular shape a crystal like this eventually takes depends entirely on the specific minerals dissolved in the water around it, and on the exact conditions, temperature, concentration, the presence of other competing compounds present at the moment each new layer forms. Some crystals growing in pools like this develop into sharp, angular structures, their faces meeting at precise, mathematical angles dictated by the underlying molecular structure of whatever mineral happens to be crystallizing. Others grow in softer, more rounded forms, clusters of smaller crystals fusing together into shapes that look, from a short distance, almost organic, more like coral than like anything typically associated with mineral deposits. The one taking shape tonight, in its own particular pool, follows a path shaped by the specific chemistry surrounding it, a combination that exists in this exact balance in vanishingly few other places on the planet's surface. This entire coloured landscape, though visually striking enough to draw researchers and photographers from around the world, represents only one part of what makes this depression so unusual. Not far from these mineral fields, in another section of the wider depression, an entirely different kind of spectacle waits, one involving not slow mineral accumulation, but something considerably more immediate and considerably more dramatic: molten rock, risen from deep within the earth, sitting open to the sky in a form found in only a small handful of locations anywhere on the planet. Rising from the flat terrain of the wider depression, a low, broad volcanic shield stands out against the surrounding landscape. Its slopes gentle enough in places to seem almost unremarkable from a distance. Nothing like the steep, dramatic cone shape most people picture when they imagine a volcano. This is Erta Ale, and what makes it genuinely unusual isn't primarily its shape or its height, modest by volcanic standards elsewhere in the world, but what can be found within a crater near its summit, an active lava lake, molten rock held open at the surface rather than sealed beneath a solid crust the way it is at the vast majority of volcanic sites found elsewhere on the planet. It's worth being precise about what makes this genuinely rare, because volcanoes themselves are not uncommon, and even active volcanoes producing visible lava are found in various locations around the world. What sets a persistent open lava lake apart is the specific and unusual combination of circumstances required to sustain one over an extended period, rather than the more common pattern of molten rock erupting briefly and then cooling and solidifying at the surface within a matter of hours or days. A true, long-lived lava lake requires a continuous supply of molten rock rising from below, roughly balanced against the rate at which the surface cools and would otherwise solidify, maintaining an open, liquid surface for months, years, sometimes considerably longer, rather than the brief, transient exposure typical of most volcanic eruptions elsewhere. Only a small number of such lakes have been documented anywhere on Earth at any given time, and their presence at any particular volcano is never guaranteed to be permanent. Lava lakes can drain suddenly, their molten contents withdrawing back into the volcanic system below over the course of hours or days, sometimes in connection with new eruptions occurring elsewhere along the same volcanic system, sometimes for reasons not yet fully understood even by researchers who have studied a particular lake closely for years. Erta Ale's own lava lake has, across the decades researchers have studied it, gone through periods of retreat and periods of renewed activity. Its exact state at any given moment, something that requires current observation to confirm, rather than something that can be assumed to hold steady indefinitely. This is worth stating plainly, because describing any natural feature as permanently, unchangingly present risks becoming inaccurate the moment conditions shift, and volcanic systems in particular are defined by exactly this kind of ongoing, unpredictable change. What can be said with confidence is that Erta Ale has, across a longer stretch of recorded observation than almost any other lava lake on the planet, maintained some form of persistent molten activity within its summit crater, making it one of the most consistently studied and consistently visited active volcanic features anywhere in the world, and one of the very few places where visitors willing to make the difficult journey can, under the right conditions, stand at the edge of a crater and look directly down into genuinely molten rock, its surface shifting and cracking in slow, hypnotic patterns, glowing orange and red beneath a thin, dark crust that continuously breaks apart and reforms as the liquid rock beneath it moves. Picture standing at the crater's rim after dark, the air around you still carrying the day's accumulated heat, even as the sky above finally darkens into true night. Below, the lava lake's surface presents itself as a dark, uneven crust, cooled just enough at contact with the air to form a thin, solid skin. But that skin is never still. It cracks continuously, thin fractures opening and spreading across the surface, each one revealing, for just a moment, the brilliant orange red of the molten rock still moving beneath. Where the cracks widen, sometimes drawing apart into genuine gaps rather than thin fissures, the color intensifies, the deep interior glow bright enough, in full darkness, to cast a visible orange light across the faces of anyone standing near the crater's edge, and bright enough to illuminate the rising column of gas and steam that drifts continuously upward from the lake's disturbed surface. The sound accompanying this scene carries its own particular character, distinct from almost anything else in this landscape. A low, continuous hiss rises from the lake's surface, punctuated occasionally by a deeper, more resonant sound, something between a groan and a distant rumble, produced as large sections of the cooled crust break apart and are drawn back down into the molten rock beneath, replaced by fresh material rising up from below to take their place. Every few minutes, sometimes more frequently, a section of crust will suddenly overturn entirely, the dark surface flipping to reveal a wide expanse of pure, glowing orange beneath, momentarily transforming a significant portion of the lake's surface before the newly exposed rock itself begins cooling and darkening, the cycle beginning again almost immediately. This constant churning reflects something fundamental about how a lava lake actually functions. Distinct from the popular image of a static pool of glowing liquid sitting quietly within a crater. The molten rock within the lake is in continuous motion, driven by convection currents not unlike those found in a pot of thick liquid heated from below, hotter material rising toward the surface at certain points, cooler, denser material sinking back down at others, the whole system circulating slowly but continuously, driven by heat rising from the magma chamber deep beneath the volcano itself. This circulation is part of what allows the lake to persist as long as it does, continuously bringing fresh, hot material up to replace whatever has cooled and solidified at the surface, rather than allowing the entire lake to simply crust over and go dark the way most exposed lava eventually does elsewhere in the world. The connection between this lava lake and the deep tectonic stretching explored earlier in this journey runs directly and unmistakably through the whole landscape. Erta Ale sits along the same rift system responsible for the depression's unusually low elevation, positioned at a point where the thinning crust allows magma an unusually direct and unusually persistent path toward the surface. In most volcanic regions elsewhere on the planet, magma must work its way up through many kilometers of thick, largely intact crust, a journey difficult and slow enough that sustained, open lava lakes remain a genuine rarity. Here, within the actively stretching and thinning crust of the Danakil Depression, that journey is considerably shorter and considerably less obstructed, part of why this particular volcano has been able to sustain some form of open, visible molten activity across a longer stretch of recorded time than almost anywhere else researchers have been able to study. Scientists monitoring Erta Ale rely on a combination of ground-based observation and satellite imagery to track the lake's condition over time, since conditions at the summit can shift meaningfully across a matter of weeks or months, periods of vigorous, highly visible activity, sometimes giving way to quieter stretches when the lake's surface crusts over more extensively, its glow reduced to a fainter presence visible only through cracks and vents rather than across a wide, open expanse. This variability is itself a valuable subject of study, offering researchers a rare, accessible window into the kind of magma movement and pressure change that, at most other volcanoes, remains entirely invisible until an eruption makes it suddenly, dramatically apparent. Local communities living within reach of Erta Ale have their own long relationship with this volcano, one reaching back further than any formal scientific study of the mountain. The name itself in the local Afar language, translates to something along the lines of smoking mountain, a description reflecting the visible plume of gas and steam that rises continuously from the summit crater, often visible from a considerable distance even when the lava lake itself remains hidden from view within the depths of the crater. For generations, this plume has served as a landmark, a fixed point of reference visible across the flat, otherwise featureless expanse of the surrounding depression, useful for orientation in a landscape that offers few other reliable markers. Reaching the summit today typically requires a demanding overnight trek across rough, volcanic terrain, often undertaken after dark, specifically to avoid the most extreme heat of the daytime hours. Guides leading small groups across ground scattered with sharp, broken lava rock, the summit itself often not reached until well after midnight. The path upward crosses terrain that shifts noticeably as elevation increases. Flat, cracked plains giving way gradually to slopes covered in older, cooled lava flows, dark rock frozen in place mid-motion, its surface twisted into ropey, folded shapes that record, in solid form, the exact way it had been moving in the moment it lost enough heat to stop flowing entirely. Some of these older flows date back decades, others considerably longer, layered one atop another across the mountain's gentle slopes, each one a record of some earlier episode of activity, now cooled and silent, waiting beneath whatever more recent flow happens to have covered it since. This timing means that most visitors experience the lava lake at its most visually striking under full darkness, when the glow of the molten rock stands in its sharpest possible contrast against the surrounding blackness, unobscured by daylight and fully able to illuminate the underside of whatever thin clouds or drifting volcanic gas happen to hang above the crater at that particular hour. Arriving at the crater's rim after such a long, dark walk carries its own particular quality. The final approach often silent except for the sound of footsteps on loose rock, until the glow becomes visible first as a faint orange smudge against the sky, then cresting the final rise, resolving suddenly into the full, direct view down into the crater itself. Standing at that crater's edge, in the deep quiet of a desert night broken only by the volcano's own low, continuous sound, it becomes possible to appreciate something the daytime landscape, with all its colour and heat and visible mineral drama, doesn't quite convey in the same way. That everything explored so far in this journey, the low elevation, the extreme heat, the mineral pools, the drifting salt, and now this open window into molten rock rising from deep within the earth, traces back to the exact same underlying cause. 3 plates, pulling slowly apart, thinning the crust beneath this landscape, allowing heat and material from deep within the planet's interior a more direct path toward the surface than almost anywhere else on Earth allows. There is a particular stillness that settles over visitors during the hours spent at the crater's rim, something distinct from ordinary quiet. Conversation tends to fade naturally the longer anyone watches the lake's surface shift and crack and reform, attention drawn entirely into the slow, hypnotic rhythm of molten rock finding its own patient equilibrium, cooling and breaking and renewing itself in a cycle with no clear beginning and no obvious end. Some visitors describe losing all sense of time during these hours. The lake's activity offering nothing resembling a clock, no predictable interval between one crack opening and the next, only a continuous, unhurried process that seems entirely indifferent to whether anyone happens to be watching it at all. The cold at this elevation after dark, modest compared to almost anywhere else but noticeable after a full day of desert heat below, adds its own quiet counterpoint to the scene. Visitors wrapping themselves against a chill that would seem entirely unremarkable elsewhere but feels here like an unexpected gift after the relentless warmth of the depression's lower ground. Stars overhead, largely undimmed by any nearby source of artificial light, spread across a sky rarely interrupted by cloud, the volcano's own faint red glow, the only earthbound light competing for attention against the wider darkness stretching out in every other direction. The glow rising from Ale's crater represents, in the most immediate and visible way this landscape offers, the same deep process responsible for the depression sinking below sea level in the first place, the same process slowly, patiently working to eventually open this stretch of Africa to the sea. Watching that glow shift and pulse in the darkness, cracks opening and closing across the lake's surface, sections of crust overturning to reveal fresh, molten rock beneath, offers about as direct a view as exists anywhere on the planet's surface into the kind of raw geological process that, across almost every other volcanic region in the world, remains hidden many kilometers beneath solid, unbroken rock. By the time the first hint of dawn begins to lighten the eastern sky, most visitors have already begun their descent back down the mountain's dark slopes, the lake's glow fading gradually behind them, still visible for a time as a faint orange smudge against the retreating night before the mountain's own bulk finally blocks it from view entirely. The walk down passes back across the same cooled, twisted lava flows climbed in darkness hours before, their full shapes and textures only now becoming visible in the strengthening morning light, dark ropes and folds of ancient rock stretching down the mountainside in patterns that will remain essentially unchanged for centuries to come, long after the current lava lake has, whenever that eventually happens, gone quiet and dark itself. Below, the wider depression begins to reveal itself again in the growing light, the same pale, flat expanse stretching toward every horizon, waiting to receive the returning travelers back into its own particular version of heat and stillness. Below the volcano's slopes, back out across the wider floor of the depression, an entirely different chapter of this landscape's story waits, one written not in fire and molten rock, but in salt, laid down across a length of time reaching back far beyond anything the volcano's own relatively recent activity can account for. That salt, and the ancient body of water responsible for depositing it, forms one of the most visually distinct and historically significant features anywhere within this remarkable stretch of ground. Stretching out from the base of the volcanic terrain, the ground changes character entirely, the dark, broken lava rock giving way, sometimes within the space of only a few hundred meters, to a landscape of almost impossible flatness, pale white in every direction, unbroken by rise or hollow for as far as the eye can follow. This is the salt flat, one of the depression's most visually distinct features, and one whose history reaches back considerably further than the relatively recent volcanic activity explored so far in this journey. The salt covering this ground did not form gradually, the way the coloured mineral deposits near the acid pools continue forming today. It formed instead through a much larger, much older process, one connected to the depression's deep geological history rather than to its current, ongoing volcanic activity. At various points across the past several million years, as the crust beneath this region continued its slow process of sinking and stretching, the depression periodically found itself connected to the nearby Red Sea, seawater flooding in to fill the low basin much as ocean water fills any newly opened low-lying terrain along a coastline. For a time, this depression held a genuine arm of the sea, its water level and its salinity governed by the same tides and currents affecting the wider ocean beyond. But the connection between the depression and the sea has never proven permanent, as the surrounding land shifted, sometimes rising slightly along the depression's margins, sometimes altering the specific channel connecting the basin to open water. That connection closed again, repeatedly, across the span of this deep history. Each time the connection closed, The seawater trapped within the depression had nowhere left to go except upward into the relentlessly dry, hot air pressing down on it from above. Evaporation, in a climate this extreme, works quickly compared to cooler, more humid regions elsewhere on the planet, and with no fresh water arriving to replace what was being lost to the air, the trapped seawater gradually concentrated, its dissolved salts becoming more and more concentrated as the water itself disappeared, until eventually nothing remained but the salt itself deposited across the basin floor in a layer that thickened with every repeated cycle of flooding and evaporation. This cycle, seawater flooding in, the connection closing, evaporation drawing the water away and leaving its salt behind, appears to have repeated itself many times across the depression's history, each repetition adding another layer to what was already accumulating beneath. Geological surveys drilling down into the salt deposits in certain parts of the depression have found layers extending to remarkable depths. Some estimates suggesting the accumulated salt reaches thicknesses of over 1 kilometre in the deepest portions of the basin, a figure that, if accurate for those specific locations, represents an extraordinary quantity of evaporated seawater condensed down across millions of years into solid mineral deposits stacked layer upon layer beneath the flat, white surface visible today. It's worth pausing on what this actually means, standing at ground level on the salt flat surface today. Every step taken across this ground passes over not simply a single, uniform sheet of salt, but potentially hundreds or even thousands of individual layers, each one representing a separate cycle of flooding and evaporation, a separate chapter in the depression's long relationship with the sea that once reached it and then withdrew, again and again, leaving this evidence behind each time. The flat, white surface visible to any visitor today is, in this sense, closer to the top page of an extraordinarily long, patient document than to a single, simple deposit laid down all at once. The flatness itself deserves attention because it's genuinely unusual, even compared to other flat landscapes found elsewhere on the planet. Evaporating water left undisturbed across a large enough surface and a long enough stretch of time naturally tends toward extreme flatness, since water itself always settles to a level surface, and whatever it deposits as it evaporates tends to follow that same level, layer after layer, building up in a uniform sheet rather than in the uneven mounds or ridges more typical of deposits formed by wind or by fast-moving water elsewhere. The result here is a surface flat enough that, standing at one edge of a large section of the flat, the horizon in every direction appears to sit at almost exactly the same height, with barely a visible dip or rise anywhere across the whole expanse. Walking out across this surface produces an experience unlike almost anywhere else. The ground underfoot is generally hard and stable, at least in the more established sections of the flat, firm enough to support the weight of loaded pack animals and, in some areas, even vehicles crossing carefully along established routes. In other sections, closer to areas where water still occasionally rises close enough to the surface to soften the salt above it, the ground can turn unexpectedly soft, a firm-looking crust concealing a layer of wet, unstable salt mud beneath, capable of swallowing a careless footstep considerably deeper than expected. Guides familiar with this terrain know precisely which sections to avoid, reading subtle differences in colour and texture invisible to an untrained eye, differences that mark the boundary between safely solid ground and ground that only appears solid from a short distance. The colour of the salt itself shifts subtly depending on the specific minerals present in whatever particular cycle of evaporation produced that section of the surface, and depending on the angle and intensity of the light falling across it at any given moment. Under the full, direct sun of midday, the flat often appears almost blindingly white, reflecting so much light back upward that visitors are advised to protect their eyes carefully, the glare intense enough to cause genuine discomfort within a short period of unprotected exposure. In the softer light of early morning or late afternoon, that same surface takes on a warmer cast, pale gold or faint pink, tinting the white as the sun sits lower in the sky. The long shadows cast by even small irregularities in the surface stretching out across the flat in ways the harsh midday light never allows. At certain times of year, when seasonal flooding briefly raises the water table beneath parts of the flat, a thin sheet of standing water can spread across sections of the surface, transforming the landscape almost overnight into something resembling an enormous, flat mirror. Under the right conditions, calm air and clear sky, this shallow water reflects the sky above with an almost perfect clarity, blurring the boundary between ground and horizon so thoroughly that visitors sometimes describe the sensation of walking through open sky itself, unable to distinguish, at a glance, precisely where the solid ground ends and the reflected image of the clouds above begins. This effect, while visually striking, is also temporary, the shallow water evaporating again within days as the same relentless heat responsible for creating the salt flat in the first place reasserts itself, drawing the water back into the dry air and leaving the surface once again hard, flat, and white. This ancient body of water, and the many cycles of flooding and evaporation responsible for building the salt layers beneath the modern surface, connects directly back to the same deep tectonic history explored earlier in this journey. Without the depression's unusually low elevation, itself a product of the crust's ongoing thinning and sagging along the boundary between three separate tectonic plates, there would have been no basin low enough for seawater to repeatedly flood into in the first place. The salt flat, in this sense, is every bit as much a product of the region's active geology as the lava lake glowing within Erta Ale's summit crater, both features tracing back to the same underlying cause, expressed here not through fire and molten rock, but through the patient, repeated accumulation of evaporated seawater across a stretch of time reaching back millions of years. For the communities who have lived within and around this depression for generations, the salt flat represents something considerably more immediate than a subject of geological curiosity. It represents a livelihood, one practiced according to methods that have remained largely unchanged for a very long stretch of time, passed down from one generation to the next through direct instruction and long practice rather than through any formal written record. The Afar people, whose traditional territory encompasses much of this depression and the surrounding highlands, have cut salt from this flat for longer than any precise historical record can confirm, developing across that time a body of practical knowledge about the salt flat's surface, its seasonal changes, and the safest routes across it that exists nowhere outside the direct experience of the people who have spent their lives working here. This knowledge covers details that might seem minor to an outside observer, but carry real consequence for anyone working on this terrain. Which sections of the flat harden reliably enough to support a loaded animal's full weight? Which sections require caution even when they appear solid? How the surface changes character depending on the season and the recent history of flooding in that particular area. Salt mining here follows a method that has changed little in its fundamentals across many generations, even as some modern tools have found their way into parts of the process. Workers move out onto the flat, typically in the cooler hours of early morning before the full heat of the day settles in, carrying tools suited to cutting through the hardened salt crust in regular, uniform blocks. The cutting itself requires a particular skill, judging by feel and experience exactly how deep to cut and at what angle in order to produce blocks that will hold together as a single, solid piece rather than crumbling apart under their own weight once lifted free of the surrounding crust. Each block, once cut, is roughly uniform in size and shape, a practical necessity given how the finished blocks will eventually be transported, stacked and balanced across the backs of camels in loads calculated carefully to distribute weight evenly and avoid overburdening any single animal. A loaded camel caravan crossing the salt flat represents one of the most enduring images associated with this landscape. A line of animals moving steadily across the flat white expanse, their dark shapes and the shapes of the workers walking alongside them standing in sharp visual contrast against the pale ground stretching in every direction around them. The physical demands of this work are considerable and worth stating plainly rather than glossing over in favor of a purely picturesque description. Workers cutting and hauling salt across this flat do so in a climate already established earlier in this journey as among the hottest average environments anywhere on the planet where people live and work on a sustained basis. The labor itself, repeated cutting and lifting of heavy salt blocks, adds its own physical strain on top of whatever burden the ambient heat already imposes. And traditional working patterns here have developed specifically around managing that combined strain, beginning work in the relative cool of early morning, resting through the most extreme heat of midday, and sometimes resuming again in the cooler hours toward evening. Water, unsurprisingly, represents one of the most critical practical concerns for anyone working on the salt flat for an extended period. The flat itself offers no natural drinking water anywhere across its surface, every drop needed for a day's work having to be carried in from elsewhere, calculated carefully against the number of workers, the number of animals, and the length of time the group expects to remain out on the flat before returning to a source of fresh water. This logistical challenge, arranging water, food, and rest across a landscape offering none of these things naturally, has shaped the traditional rhythm of salt mining here as thoroughly as the chemistry of evaporation shaped the salt deposits themselves. Beyond the physical labor of cutting and hauling, the broader trade in Danakil salt has, across a long history, connected this remote depression to a much wider economic network extending across highland Ethiopia and beyond. For centuries, before modern transportation infrastructure reached into this part of the country, salt cut from this exact flat traveled by camel caravan along established routes leading up out of the depression and into the Ethiopian highlands, where it was traded for grain, livestock, and other goods unavailable within the depression itself. Salt blocks of a standardized size, cut according to traditions specific to this region, functioned at various points in history as a form of currency in their own right, their value understood and accepted across a trade network reaching considerably further than the depression's own immediate borders. Some of that traditional trade continues today, even as modern transportation has, in various ways, altered the broader economics surrounding it. Trucks now handle a portion of the salt's journey out of the depression along routes accessible to vehicles, a development that has changed some aspects of the trade while leaving the fundamental work of cutting the salt itself largely unchanged, still performed by hand, still governed by the same practical knowledge of the flat surface passed down across generations. Watching this work in progress, the rhythmic motion of workers cutting through the crust, the careful stacking and balancing of blocks onto waiting animals, the slow, patient procession of a loaded caravan setting off across the flat toward the distant highlands offers a particular kind of insight into this landscape that its geology alone cannot fully provide. The salt flat is not simply a geological curiosity, a record of ancient seas evaporating across millions of years. It is also, and has been for a very long time, a working landscape, one that has supported human life and human trade, despite conditions that would make sustained habitation genuinely difficult almost anywhere else on the planet. There is something worth sitting with in the particular relationship this work represents, between people and a landscape that offers so little in the way of obvious welcome. The heat here does not soften for the sake of the workers moving across it each morning. The flat offers no shade, no water, nothing beyond the salt itself and the flat, hard ground supporting it. And yet generations of people have found, within exactly these conditions, Not simply a means of survival, but an entire way of life, one built around a deep, practical understanding of a landscape that continues, even now, to demand the same careful respect it has always required from anyone attempting to work within it. As the sun climbs higher over the flat and the morning's work draws toward its natural pause, the heat building toward its full daytime intensity, the loaded caravans already beginning their slow journey back toward higher ground, it's worth turning attention toward a different kind of resident of this landscape entirely, one far smaller than any human worker or camel, and yet, in its own way, every bit as remarkable in its ability to endure conditions that would overwhelm almost any other form of life found elsewhere on the planet. Within the acidic pools scattered across the mineral fields explored earlier in this journey, in water hot enough to make prolonged contact dangerous and acidic enough to dissolve materials that would resist far milder conditions elsewhere, something continues to live. Not simply survive in some marginal, barely clinging on sense, but genuinely live, reproduce, and in certain cases thrive. In water, most living things found elsewhere on the planet would find lethal within moments of contact. These organisms are almost entirely microscopic, invisible to the naked eye except in the aggregate, where their combined presence sometimes tints the water or the mineral crust surrounding a pool with a faint color distinct from what pure chemistry alone would produce. A patch of unusually vivid green along a pool's edge, a faint reddish tinge spreading across an otherwise pale mineral crust. These visual details, easy to attribute entirely to mineral chemistry at first glance, sometimes owe at least part of their color to the presence of living organisms clustered densely enough to leave their own visible trace on the landscape around them. Researchers sampling these pools have learned to look for these subtle color variations as one small clue, among many, pointing toward where a particular pool's population of microscopic residents happens to be most concentrated at any given time. Scientists refer to organisms capable of surviving in conditions this extreme as extremophiles, a broad term covering life adapted to environments defined by conditions once assumed, earlier in the history of biology, to make life of any kind essentially impossible. Extreme heat, extreme acidity, extreme salinity, extreme pressure. The Danakil Depression, in its own particular combination of these factors, has become one of the most studied natural laboratories anywhere on the planet for understanding exactly how life manages to persist under circumstances this hostile. To appreciate why this matters, it helps to step back briefly and consider what biology, for a long stretch of its own history as a scientific field, generally assumed about the limits of life. For much of that history, researchers operated under the reasonable assumption that life required conditions falling within a relatively narrow, moderate range. Water that was neither too hot nor too acidic, temperatures compatible with the kind of chemistry cells used to build and maintain themselves, environments offering enough stability that the delicate molecular machinery underlying all known life could function without being torn apart or denatured by conditions too far outside its comfortable operating range. Discoveries across the past several decades, in locations including this depression but also deep ocean vents, Antarctic ice, and various other extreme environments scattered around the planet, have steadily expanded that assumed range considerably further than earlier researchers believed possible. Organisms have now been documented surviving, and in some cases actively thriving, in water hot enough to boil at normal atmospheric pressure, in acidity levels close to those of industrial cleaning agents, in salt concentrations far beyond what most cells can tolerate, and in combinations of these extreme factors occurring simultaneously, exactly the kind of layered, compounding hostility found within many of the pools scattered across this particular landscape. The specific organisms documented within the Danakil Depression's most extreme pools include various forms of archaea, a distinct branch of microscopic life, separate from both the more familiar bacteria and from the more complex cells making up plants, animals, and fungi. Archaea, as a broader category, have proven particularly well represented among extremophiles studied around the world, their cellular chemistry apparently better suited, in ways researchers continue actively studying, to tolerating the kind of extreme heat, acidity, and salinity found in environments like this one. Alongside various archaea, researchers working in this depression have also documented certain specialized bacteria capable of surviving within the same harsh pools, each species representing its own particular set of adaptations, allowing it to maintain the basic functions of life within conditions that would rapidly destroy the cellular structure of almost any more conventional organism. Picture, for a moment, what survival actually requires within one of these pools. The cellular membrane surrounding any living cell must remain intact and functional even when surrounded by water acidic enough to strip away the protective structures most cells rely on. The proteins responsible for carrying out essential chemical processes within the cell must fold correctly and remain stable even at temperatures that would cause most proteins to unfold and lose their functional shape entirely, a process called denaturation that effectively destroys a protein's ability to perform its intended role. And all of this must happen continuously, cell after cell, generation after generation, in an environment offering no relief, no cooler or less acidic refuge nearby to retreat toward when conditions become momentarily too extreme. Consider, too, the genetic material every one of these cells depends on to reproduce and pass its particular adaptations forward into the next generation. In conditions this extreme, ordinary genetic material would face constant risk of damage. The same heat and acidity capable of unfolding proteins, equally capable of disrupting the delicate molecular structure carrying a cell's genetic instructions. The organisms that manage to persist here have developed their own particular solutions to this challenge as well, repair mechanisms and structural adaptations that help protect their genetic material against the kind of damage that would, in a more conventional organism, accumulate rapidly enough to prevent successful reproduction altogether. The organisms that have managed to solve these challenges have done so through adaptations built up gradually across an extremely long evolutionary history. Adjustments to the fundamental chemistry of their cell membranes, their proteins, and their genetic material, each adaptation representing a slow, incremental improvement in tolerance, accumulated across countless generations reaching back long, before anything resembling the modern landscape of this depression existed in its current form. Some of these adaptations involve specialized lipids, the fatty molecules forming the basic structure of a cell's outer membrane, built in these organisms according to a chemical architecture considerably more stable under extreme heat and acidity than the equivalent structures found in more conventional cells. Others involve specialized proteins capable of maintaining their functional shape, even under conditions that would cause an ordinary protein to unravel, sometimes assisted by additional molecules whose entire function seems to be stabilizing other, more vulnerable components of the cell against the surrounding environment's relentless hostility. Researchers collecting samples from these pools typically work with considerable care, both for their own safety, given the genuine hazards the water itself presents, and for the integrity of whatever organisms they hope to study, since many of these extremophiles prove difficult to keep alive once removed from the exact conditions they've adapted to, a reminder that their remarkable tolerance for extremity applies specifically to the particular combination of heat, acidity, and mineral content found within their home pool, rather than representing some general, all-purpose hardiness capable of surviving any condition whatsoever. What makes this depression particularly valuable as a site for this kind of research isn't simply that extreme life exists here, since extremophiles have now been documented in various extreme environments scattered around the world. It's the particular combination and concentration of extreme conditions found within a relatively compact, accessible area, extreme heat, extreme acidity, and high salinity all occurring together, sometimes within pools situated only a short distance from one another, allowing researchers to study a range of extreme adaptations without needing to travel between environments separated by vast distances, or requiring entirely different logistical approaches to reach safely. This concentration of extreme conditions within a single, relatively contained landscape connects directly to the depression's deep geological history explored earlier in this journey. The same tectonic stretching responsible for the region's unusually low elevation, its extreme heat, and its ongoing volcanic activity has also produced the particular chemistry feeding these pools. Mineral-rich water rising from deep underground, heated by proximity to magma, carrying with it the dissolved salts and acids that give each pool its own particular character. Without that underlying geological activity, none of the specific conditions supporting this concentration of extremophile life would exist in anything like their current form. It's precisely this combination of factors, extreme heat, extreme acidity, unusual mineral chemistry, and life persisting despite all of it, that has drawn attention from an entirely different scientific community. One focused less on understanding the limits of life here on Earth and more on understanding what those limits might suggest about the possibility of life existing, or having once existed, on other worlds entirely. Researchers affiliated with NASA and various other space agencies and astrobiology research institutions have, across recent decades, conducted repeated fieldwork within the Danakil Depression, drawn by a landscape whose surface chemistry and physical conditions bear a closer resemblance to certain regions of Mars than almost anywhere else easily accessible on Earth. This comparison deserves careful, precise treatment, because claiming a location on Earth is simply, like Mars, risks collapsing a genuinely useful scientific analogy into a vague, exaggerated soundbite. The value of this landscape to Mars research lies in specific, testable similarities rather than in any broad, general resemblance between one dry, harsh landscape and another. Mars, based on evidence gathered by orbiting satellites and by rovers that have explored its surface directly, appears to have once hosted liquid water, likely including bodies of water shaped by volcanic and hydrothermal activity, not unlike what continues occurring within this depression today. Certain regions of the Martian surface show mineral signatures, particular combinations of sulfur compounds, iron oxides, and other minerals that closely resemble the mineral deposits found around this depression's acid pools and hydrothermal fields. Studying exactly how these minerals form here on Earth, under conditions researchers can observe and measure directly, offers a valuable model for interpreting similar mineral signatures detected remotely on Mars, where direct, close-up study remains vastly more difficult and expensive to conduct. The specific mineral most often discussed in this comparison is sulfur itself, along with the particular family of iron-bearing minerals that form when iron-rich water reacts with oxygen at the surface. Minerals researchers have identified in significant quantities across various regions of the Martian surface photographed by orbiting spacecraft and studied directly by ground-based rovers. On Earth, within this depression, researchers can walk directly up to deposits of these exact minerals, sample them, measure the precise temperature and acidity of the water that produced them, and observe in real time the ongoing processes still actively building new layers of similar material today. On Mars, by contrast, researchers must work entirely from a distance, interpreting spectral data gathered by orbiting instruments or images and limited chemical analysis conducted by a rover exploring only a small fraction of the planet's surface, a considerably more constrained and indirect form of study than anything available here in the Danakil Depression. Beyond the mineral chemistry itself, the presence of extremophile life within this depression's most hostile pools offers researchers a valuable framework for thinking about where, specifically, evidence of past or present life might be found if it exists anywhere on Mars. If life can persist within acidic, mineral-rich, geothermally heated pools here on Earth, the reasoning goes, then similar environments on Mars, assuming they existed with anything like sufficient duration and stability, might plausibly have supported comparable forms of life at some point in that planet's history, particularly during periods when Mars appears to have held more liquid water at or near its surface than it does today. This is worth stating with appropriate caution, because the presence of extremophile life in a Mars analog environment on Earth does not, on its own, demonstrate that life ever existed on Mars itself. What it does provide is a scientifically grounded basis for forming testable hypotheses, for identifying the specific kinds of mineral signatures or chemical traces that past microbial life, if it existed on Mars, might plausibly have left behind. Signatures researchers can then specifically search for within data gathered by Mars rovers and orbiters. In this sense, the Danakil Depression functions less as a direct stand-in for Mars and more as a kind of natural laboratory, a place where hypotheses about the chemistry and biology of extreme, Mars-like environments can be tested and refined under conditions researchers can observe and sample directly before those refined hypotheses are applied to the considerably more difficult and indirect task of interpreting evidence gathered from another planet entirely. Fieldwork conducted within this depression by astrobiology researchers has typically focused on several specific lines of investigation. One involves detailed sampling and analysis of the mineral deposits surrounding the acid pools, comparing their precise chemical composition and physical structure against similar mineral signatures identified on Mars, looking for close matches that might help confirm or refine current understanding of how those Martian minerals originally formed. Another involves close study of the extremophile organisms themselves, examining the specific molecular adaptations allowing them to survive conditions this extreme, research that contributes both to the broader scientific understanding of life's fundamental limits and to more specific hypotheses about what kind of biological signatures, if any, might be detectable within samples eventually returned from Mars by future missions. A further line of research focuses on the physical processes shaping this landscape more broadly, the mineral deposition patterns, the specific ways evaporating, mineral-rich water builds up layered deposits over time, patterns that researchers can compare directly against surface features photographed and analysed by Mars rovers exploring similarly dry, mineral-rich terrain on that distant planet. Understanding precisely how a particular mineral pattern forms here on Earth, under conditions available for direct observation, helps researchers interpret similar patterns observed remotely on Mars with considerably greater confidence than would be possible without this kind of terrestrial comparison to draw upon. The practical challenges of conducting this research within the Danakil Depression mirror, in certain respects, the very challenges that make the landscape scientifically valuable in the first place. Researchers working here must contend with the same extreme heat, the same difficult access, and the same hazardous pools that shape every other aspect of human interaction with this landscape, wearing appropriate protective equipment when sampling acidic water directly, timing fieldwork carefully around the most extreme hours of daytime heat, and relying on the same kind of local knowledge and guidance that has allowed communities and travelers to navigate this terrain safely for generations. In this sense, the scientific study of this landscape as a Mars analogue connects directly back to the same themes explored throughout this journey so far: extreme conditions demanding careful, respectful engagement, whether from a salt worker cutting blocks from the flat at dawn or a researcher collecting water samples from beneath the rim of an acid pool. There's something worth sitting with in the idea that this landscape, shaped by processes entirely specific to Earth's own particular geological history, 3 tectonic plates slowly pulling apart, a crust thinning and sagging above a stretch of rising magma, has become one of the more valuable places on this planet for understanding conditions on a world tens of millions of kilometers away. Nothing about the depression's formation had anything to do with Mars specifically, and yet the particular combination of heat, chemistry, and geological activity converging here happens to closely echo conditions researchers believe once existed, and in some more limited form may still exist across parts of that distant, cold, dry planet. This connection between one of the most remote, hostile landscapes on Earth and the ongoing search for evidence of life beyond our own planet adds a further layer of significance to a place already remarkable for its geology, its heat, its color, and its deep human history of salt trade and careful survival. Every pool sampled here, every mineral deposit analyzed, every extremophile organism identified and studied contributes in some small way to a much larger, ongoing scientific effort extending far beyond the boundaries of this particular depression. An effort seeking to understand not simply how life persists under extreme conditions here on Earth, but how and where it might exist, or might once have existed, on worlds considerably further from home. Beyond the acid pools and their microscopic residents, elsewhere across this same landscape, an entirely different kind of geological feature continues its own quiet activity, one built not from lava or from the slow accumulation of evaporated seawater, but from mineral-rich water rising directly from deep underground, forming intricate, colourful terraces and formations found in only a small number of locations scattered across the entire planet. Near the northern reaches of the depression, close to where the salt flat gives way once again to ground shaped more directly by volcanic and geothermal activity, a site known as Dalol rises gently from the surrounding plain, its low, uneven terraces built entirely from mineral deposits laid down by hot springs that continue, even now, to seep and bubble up from somewhere deep beneath the surface. If the acid pools explored earlier in this journey represent this landscape's most vivid demonstration of chemistry made visible, Dalol represents something even more concentrated still, an entire hillside built almost entirely from the accumulated mineral residue of water that has been rising, cooling, and depositing its dissolved contents here for a very long stretch of time. The name itself carries its own quiet significance, drawn from the Afar language and often translated as something close to dissolution or disintegration. A fitting description for a landscape built entirely from the slow, patient dissolving and redepositing of mineral matter, water carrying salt and sulfur and iron up from deep underground only to release it again at the surface over and over, in a cycle stretching back long before anyone gave this particular hillside its current name. Some of the earliest written accounts of this site, left behind by travelers and early geological surveyors passing through the region generations ago, describe encountering the formations here with a mixture of fascination and genuine unease, uncertain at first glance whether they were looking at a natural landscape at all or at the remains of some collapsed and long abandoned structure. Approaching Dalol from a distance, the terrain rises only slightly above the surrounding flat, low mounds and terraces spreading outward in irregular, overlapping patterns, their surfaces catching the light in a way that immediately sets them apart from the pale salt flat stretching away on every side. Closer still, the full range of colour becomes apparent, greens deepening toward near turquoise in certain pools, yellows sharpening into something closer to gold where sulfur concentrations run particularly high, patches of white and pale pink marking areas where a different mineral balance has produced its own distinct deposit. Nothing about this palette repeats itself in quite the same combination anywhere else. The specific mix of colours at Dalol, shaped by a particular chemistry, found in only a small handful of comparable sites scattered around the planet. The springs feeding this landscape draw their water and their heat from the same deep geological processes responsible for everything else explored so far in this journey. The thinning crust, the rising magma, the ongoing tectonic stretching pulling this stretch of Africa slowly apart. As groundwater percolates downward through cracks and fissures in the rock, it encounters heat rising from magma sitting relatively close to the surface in this particular part of the depression, warming considerably as it does and dissolving an increasing quantity of minerals from the surrounding rock the longer and the hotter that contact continues. By the time this heated, mineral-saturated water finds its way back up toward the surface, rising through whatever fractures happen to offer it a path. It carries within it a concentrated cocktail of dissolved salts, sulfur compounds, iron, and various other elements, each one ready to precipitate out and form a solid deposit the moment conditions at the surface, cooler temperature, exposure to air, change the water's chemistry enough to force those dissolved minerals to settle out of solution. This journey the water takes, from rainfall or ancient trapped moisture sinking slowly downward through increasingly hot rock, and finally back up toward daylight carrying its dissolved cargo of minerals, can take anywhere from a matter of years to considerably longer, depending on the specific depth reached and the particular path followed through the fractured rock underlying this section of the depression. Some of the water surfacing at Dalol today may have begun its underground journey only recently in geological terms, while other portions may represent water that has been circulating through this deep system for a considerably longer stretch of time, each molecule carrying its own particular, unknowable history of contact with hot rock and dissolved mineral before finally emerging, however briefly, into open air. This precipitation happens continuously in small increments, water seeping up through a particular vent, spreading briefly across the surface, losing enough heat and enough dissolved gas to force a portion of its mineral content out of solution, and then either evaporating entirely or draining onward to the next low point, leaving behind a thin, fresh deposit with each individual pulse. Repeated over years, then decades, then centuries, these countless small depositions build up into the terraces and mounds visible today, shaped not by any single dramatic event, but by an accumulation so gradual that no single moment of its construction would ever have looked like anything more than a small, unremarkable trickle of warm, coloured water spreading briefly across already coloured ground. The specific shapes these terraces take reflect the particular way mineral-laden water moves across an already irregular surface, pooling briefly in small depressions, overflowing gradually toward the next lower point, building up rims and small dams of solid mineral deposit along whatever edge happens to mark the boundary of each temporary pool. Over enough time, this process produces the kind of layered, terraced formations visible at Dalol today, structures that bear a certain resemblance to similar formations found at hot spring sites in other volcanically active regions of the world, though the specific mineral chemistry here, shaped by this depression's particular combination of underlying salt deposits and volcanic heat, produces a color palette and a mineral composition distinct from comparable sites found elsewhere. Some of these terraces have grown into shapes resembling small, irregular staircases, each step marking a boundary where mineral deposit built up faster than the water above it could overflow, forcing a new, slightly higher pool to form before eventually breaching its own rim and continuing the pattern downward. Others have taken on rounder, more bulbous forms, built up where water seeped more evenly across a broader area rather than channeling through any single dominant path. Walking among these different shapes, it becomes possible to read, with a little practice, something of the specific history of water flow that produced each particular formation, steep, narrow terraces suggesting a strong, concentrated flow from a single vent, broader, gentler mounds suggesting water that spread more evenly across a wider stretch of ground. Walking among these formations requires the same kind of careful attention demanded elsewhere across this landscape's more hazardous terrain. Some pools sit shallow and relatively cool, safe enough to approach closely and observe in detail. Others carry water hot enough and acidic enough to present a genuine hazard, their surface offering little visible warning of the temperature or chemistry lurking just beneath. Guides leading visitors through this particular section of the depression rely on the same accumulated local knowledge that governs safe passage across the salt flat and around the acid pools explored earlier, knowledge built from direct, repeated experience rather than from any formal survey or published hazard map. The ground itself, in certain stretches between the more prominent terraces, carries its own particular fragility. Thin crusts of mineral deposit, sometimes concealing softer, wetter material immediately beneath, a hazard requiring the same practiced eye for subtle color and texture variation described earlier in relation to the salt flat's own occasionally treacherous surface. Guides moving through this terrain tend to test unfamiliar ground carefully before committing their full weight to it. A habit built from long experience rather than from any particular nervousness, and visitors are encouraged to adopt themselves rather than trusting entirely to the apparent solidity of ground that, in this landscape more than almost anywhere else, can prove considerably less stable than its surface appearance suggests. The gases rising continuously from various vents scattered across this hydrothermal field add their own dimension to the experience of moving through this landscape. Steam mixes with sulfur dioxide and other volcanic gases, producing a faint haze that hangs close to the ground in certain sheltered pockets, particularly in the cooler hours of early morning before rising heat disperses it more thoroughly into the wider air. The smell, sharp and mineral, carries a particular intensity here that even the acid pools explored earlier in this journey rarely quite match. A reminder that this entire hillside sits directly above one of the more concentrated points of geothermal activity found anywhere within the wider depression. Certain gases escaping from these vents carry genuine hazard alongside their visual and olfactory presence. Concentrations of sulfur dioxide and other volcanic gases occasionally building to levels requiring real caution, particularly in low-lying pockets where heavier gases can settle and linger rather than dispersing freely into open air. Visitors and researchers working closely around these vents typically monitor wind direction carefully, positioning themselves upwind of active gas sources whenever possible. Another small but essential piece of practical knowledge required to move safely through a landscape that offers its striking visual rewards alongside genuine, ever-present risk. Small pools scattered among the terraces sometimes bubble gently and continuously, gas escaping from deep underground, finding its way up through the standing water and breaking the surface in a slow, irregular rhythm. In certain pools, this bubbling occurs steadily enough to keep the surface in near constant, gentle motion, small ripples spreading outward from each release point and crossing paths with ripples from neighboring vents, producing a complex, shifting pattern across water otherwise still enough to reflect the sky and the colored terraces surrounding it with considerable clarity during calmer moments. Between releases, a patient observer watching one particular pool for long enough begins to notice its own individual rhythm, distinct from the pool beside it, each one keeping its own quiet, irregular time according to whatever specific conditions govern the vent feeding it from below. Listening closely near one of these more active pools, a visitor can pick out a whole small symphony of sound easy to miss at first, the soft, wet pop of individual gas bubbles breaking the surface, a faint, continuous hiss where steam escapes more steadily from a nearby vent, and, underlying everything else, an almost imperceptible low hum some visitors describe hearing, or perhaps simply feeling, through the ground itself, a vibration connected to the same deep, ongoing geological activity responsible for every other feature of this remarkable landscape. Researchers studying this particular site have paid close attention to the specific sequence in which different minerals deposit as the rising water cools and loses its dissolved gases, since that sequence offers a detailed record of the exact chemical conditions present at each stage of the water's journey from deep underground back to the surface. Sulfur tends to precipitate first at the hottest points closest to each vent, while other minerals settle out further along the water's path as it continues cooling, creating a rough, readable gradient of color and mineral type stretching outward from each active spring. A gradient any careful observer can trace simply by walking from the hottest, most active point outward toward the cooler, quieter margins of the field. This kind of detailed chemical mapping serves multiple purposes at once, contributing both to a broader scientific understanding of how hydrothermal systems function in general, and to the more specific Mars analog research explored earlier in this journey, since similar sequences of mineral deposition, if identified within data gathered from the Martian surface, could offer valuable clues about the history of water and heat on that distant planet as well. There is a particular quality to the atmosphere at Dalol that visitors often describe as feeling more alien than almost anywhere else within this already unusual depression. A landscape built entirely from mineral deposit, offering no vegetation, no shade, nothing resembling the ordinary textures and colors associated with terrestrial landscapes elsewhere on the planet. Standing among the terraces at certain hours, particularly as the light shifts through the earlier and later parts of the day, the whole scene can take on an appearance closer to something imagined than something naturally occurring. Colors and textures arranged in patterns that feel, despite their entirely natural origin, somehow deliberate, composed, as though shaped by an aesthetic sensibility rather than by the blind, patient accumulation of mineral-laden water finding its way to the surface over countless small pulses across a very long stretch of time. Photographs taken of this landscape, viewed by people who have never visited in person, sometimes prompt genuine disbelief that the colors and formations shown could exist naturally, without some degree of artificial enhancement or alteration. Researchers and guides familiar with the site have grown accustomed to this reaction, understanding that nothing about ordinary human experience, shaped by landscapes considerably more conventional in their color and texture, prepares a person for what this particular hillside actually looks like in person. Sunlight falling directly across mineral formations built from a chemistry found in only a small number of comparable locations scattered across the entire planet. Beneath all of this color and heat and slow mineral accumulation, the same fundamental process explored earlier in this journey continues its work, largely invisible to anyone standing at the surface, and yet responsible, ultimately, for every feature of this landscape described so far. The crust beneath the Danakil Depression continues, even now, to stretch and thin and sag, the three tectonic plates meeting beneath this region, pulling steadily apart from one another at a pace too slow to notice directly, but fast enough, measured across the scale of geological time, to be actively reshaping this stretch of Africa with each passing year. It helps, in trying to picture this ongoing movement, to set aside any comparison to processes operating on a human timescale entirely. The plates beneath this depression move apart from one another at a rate generally estimated at somewhere between 1 and 2 centimeters per year, a figure that, stated plainly, sounds almost too small to matter at all. And yet this same rate of movement, sustained consistently across 1 million years, would produce a separation measured in tens of kilometers, and sustained across the many millions of years, geologists believe this particular rifting process has already been underway, has already produced the substantial, measurable thinning and sinking responsible for the depression's current depth below sea level. Researchers monitoring this ongoing process rely on a combination of tools to track exactly how the ground here continues to change. Satellite-based measurements, capable of detecting ground movement on the scale of mere millimeters, have confirmed that certain sections of the depression continue sinking gradually, the crust beneath these areas thinning further as the tectonic plates above it continue their slow separation. Ground-based instruments, positioned at fixed points across the depression and monitored over extended periods, provide additional confirmation, tracking small but consistent shifts in position that, summed across years and decades, reveal the true scale of the ongoing geological activity happening beneath this apparently static, unchanging landscape. This sinking has not occurred, and does not continue to occur at a uniform rate across the entire depression. Certain sections, particularly those closest to the most active volcanic and hydrothermal centers like Erta Ale and Dalol, appear to be sinking and stretching somewhat more rapidly than other, more geologically stable portions of the wider basin. This uneven pattern reflects the underlying complexity of the tectonic processes at work here. The crust beneath this region not simply pulling apart evenly along a single, clean line, but rather stretching and fracturing in a more complicated, distributed pattern, different sections responding differently depending on the specific local geology and the particular arrangement of fault lines and fractures running beneath that section of ground. Earthquakes, though generally modest in scale compared to the more dramatic seismic events associated with plate boundaries elsewhere on the planet, occur with some regularity throughout this region, each one representing a small, sudden release of the accumulated stress built up as the crust here continues its slow, ongoing stretching. Most of these earthquakes pass entirely unnoticed by anyone not equipped with sensitive seismic monitoring instruments, their magnitude too small to produce any noticeable shaking at the surface. Occasionally, though, larger events occur, sometimes accompanied by visible surface changes, new cracks opening along the ground, existing fractures widening slightly, small sections of terrain shifting in ways that leave a lasting, visible mark on the landscape. For communities living within and around this depression, these small, frequent tremors have become simply another familiar feature of life in a landscape defined, in almost every respect, by geological activity operating close to the surface. Long experience has taught residents to distinguish between the ordinary, harmless background rumble that occurs with some regularity and the rarer, more significant event that might warrant genuine caution. Knowledge built the same way as the practical understanding of safe salt cutting routes or safe distances from the most dangerous acid pools through direct, accumulated experience passed down across generations rather than through any formal seismological training. Volcanic activity across the wider region follows its own related rhythm. Periods of relative quiet interspersed with episodes of renewed activity, sometimes at Erta Ale itself, sometimes at other volcanic centers scattered across the wider Afar region beyond the boundaries of the depression proper. Researchers have documented, across the past several decades, various episodes of significant volcanic and seismic activity within this wider region, including at least one notable episode during which a substantial section of the rift system experienced rapid, dramatic widening over the course of just a few days, accompanied by significant volcanic activity and a swarm of earthquakes considerably more intense than the region's usual, quieter background level of seismic activity. Events of this kind offer researchers valuable, concentrated windows into the same ongoing process of continental rifting that, across the much longer span of geological time, has been slowly shaping this entire depression since long before anything resembling its current landscape existed. Such episodes, while rare within any single human lifetime, offer a useful reminder that the deep, patient stretching described throughout this journey does not always proceed at a perfectly steady, imperceptible pace. Occasionally, accumulated stress along a particular section of the rift releases more suddenly than usual, producing, within the span of days rather than millennia, a burst of change considerably more dramatic than the typical gradual rate of movement measured by satellite instruments across ordinary years. These episodes remain, even at their most dramatic, small compared to major earthquakes associated with more actively colliding plate boundaries elsewhere on the planet, but within the specific context of this rift system's usual, quiet pace, they stand out as genuinely significant events, closely studied by researchers eager to understand precisely how this long, slow process of continental separation actually unfolds in practice, rather than simply in theory. Looking toward the future, and here it's worth being appropriately careful about the specific scale of time involved, researchers studying this region generally agree that the ongoing stretching and thinning of the crust beneath the Danakil Depression represents an early stage in a much longer process of continental rifting, one that, should it continue at anything resembling its current pace and pattern, would eventually result in this section of Africa fully separating from the rest of the continent, allowing water from the nearby Red Sea to flood permanently into the resulting gap and beginning the formation of an entirely new ocean basin. This is not a prediction of change occurring within any time frame meaningful to human planning or human memory. The processes involved operate across a timescale of millions of years, and estimates for when a fully connected, permanent seaway might eventually form here vary considerably, depending on the specific model and assumptions used, with most serious estimates placing that eventual outcome well beyond any time frame relevant to the current landscape, its current communities, or indeed to human civilization. As it exists today, it is a future measured not in generations or even centuries, but on a scale that renders such units nearly meaningless, a future belonging entirely to the deep, patient rhythm of geological time rather than to anything resembling ordinary human experience of change and continuity. What can be said with greater confidence is that this depression represents one of the relatively few places on the planet's surface where the earliest stages of this kind of continental rifting process are directly observable, studyable, and ongoing, rather than existing only as a historical process reconstructed from ancient rock formed long ago. Elsewhere in the world, similar rifting processes either finished long ago, leaving behind an already formed ocean basin whose active, formative stage has long since passed, or remain hidden beneath layers of rock and sediment too deep and too inaccessible for the kind of direct, ground-level observation possible here. The Danakil Depression, by contrast, offers researchers an active, visible, still unfolding example of exactly the kind of process that has, across the vastly longer span of the planet's full geological history, been responsible for opening every ocean basin currently found anywhere on Earth's surface, including the oceans separating the very continents most of us call home today. Few landscapes anywhere offer quite this same opportunity, to stand at ground level and observe, directly and without needing to reconstruct anything from ancient, long-cooled rock, the earliest visible stages of a process that will, eventually, redraw the map of an entire continent. There is something worth sitting with in this idea, standing among the coloured terraces of Dalol, or looking out across the flat expanse of the surrounding salt plain. That the ground beneath your feet, however solid and unchanging it feels in this particular moment, is in fact actively, if imperceptibly, in motion, part of a process that will, given enough time, transform this entire landscape into something entirely different from what it is today. The hot springs, the acid pools, the salt flat, the distant glow of Erta Ale's lava lake, all of it exists at this exact moment within a single, brief chapter of a much longer story, one that began millions of years ago as three pieces of the planet's crust first began pulling apart from one another, and one that will continue, patiently, indifferently, for millions of years still to come, long after. Every feature described so far in this journey has changed beyond easy recognition. It's worth considering, too, what this depression might eventually look like should this process continue on its current trajectory across the vast stretch of future time available to it. A gap opening gradually along the line of greatest weakness in the thinning crust, seawater from the nearby Red Sea beginning to intrude further and further inland, first as occasional flooding during periods of unusually high tide or storm surge, then as the connection widens and deepens as a more permanent arm of the sea, submerging the salt flats, the acid pools, and eventually even the terraces of Dalol itself beneath water considerably deeper and considerably more permanent than anything that has flooded this basin during its past cycles of temporary connection and withdrawal. The volcanic activity currently visible at the surface would likely continue in some form even after this transition, many of the world's active volcanoes today sitting along precisely this kind of submerged or partially submerged rift boundary, magma continuing to rise and interact with seawater in ways that would produce their own distinct geological features, different in character from anything currently visible within the dry depression, but connected by the exact same underlying tectonic process. As the heat of the day settles more fully across the depression, the light beginning its slow shift toward the softer, longer shadows of late afternoon, the terraces of Dalol take on yet another subtle shift in color and character, the same deep processes that built this landscape continuing their quiet work beneath a surface that, to anyone simply passing through, offers only the barest hint of just how much is happening, layer by layer, mineral by mineral, beneath its colorful, deceptively still exterior. As the sun finally drops below the low ridges surrounding the depression, the whole landscape begins a transformation almost as dramatic, in its own quiet way, as anything encountered earlier in this journey. The heat that has pressed down across the ground since early morning starts to lift, releasing slowly into a sky already deepening from pale blue toward a richer, darker shade, the first faint stars beginning to show themselves in the gaps between wherever thin cloud happens to drift overhead. The ground itself, having absorbed the day's full measure of heat, continues radiating warmth back upward for some time after the sun has gone. A lingering presence felt most clearly through the soles of bare or lightly covered feet, a reminder that cooling here happens gradually rather than all at once. But gradually, hour by hour, the temperature does fall, the fierce, relentless heat of midday giving way to something more bearable, then eventually to something almost cool by comparison, a shift substantial enough that many who work across this depression time, their most demanding tasks specifically around these easing evening hours. Sound changes too as the light fades. The faint hiss of gas vents and the soft, wet pop of bubbles breaking across the acid pools continue much as they have throughout the day, indifferent to the passage from light into darkness. But the wider silence surrounding those sounds deepens, the shimmer and distortion of heated daytime air settling into something calmer, clearer, allowing sound to carry further across the flat, open ground than it does during the more turbulent hours of full sun. Above the salt flat, once full darkness settles in, the sky reveals itself with a clarity rarely matched anywhere, with greater humidity or greater artificial light nearby to compete with it. Stars spread in genuine abundance across the whole visible dome overhead, the Milky Way itself, often visible as a distinct pale band stretching from one horizon to the other, undimmed by the kind of atmospheric haze or light pollution that obscures this view across so much of the rest of the inhabited world. Standing on the flat white surface beneath this sky, the ground beneath still faintly pale even in darkness, reflecting back whatever starlight reaches it, the whole scene can feel less like standing on a desert floor and more like floating somewhere between two mirrored fields of stars, one fixed overhead, the other spread quietly underfoot. In the distance, toward the volcanic ridge holding Ail's summit, a faint orange glow sometimes remains visible against the darker silhouette of the mountain, a quiet counterpoint to the cooler, whiter light scattered across the sky above. Anyone who has spent the earlier hours of this journey standing at that crater's edge, watching the lava lake's surface crack and reform, understands exactly what that distant glow represents. The same molten rock still moving, still churning, indifferent to the hour, indifferent to whether anyone remains nearby to watch it. From this distance, across the flat, dark expanse of the salt plain, that glow becomes something closer to a single, steady point of reference, a reminder of the deep heat continuing to rise from below even as the surface elsewhere across the depression grows steadily cooler with each passing hour of night. Communities living within reach of the depression settle into their own particular version of evening at this hour, the demanding work of the daylight hours, salt cutting, herding, the long walks between one water source and the next, easing into a quieter rhythm shaped by cooking fires and conversation, voices carrying easily across the still night air in a landscape that offers so little else to absorb or interrupt sound. Children who have grown up within this terrain know its night sky the way children elsewhere might know the layout of a familiar room, unremarkable to them in its abundance, simply the sky as it has always looked, every night, for as long as anyone in their family can remember. Within one of the pools scattered across the depression's mineral fields, the crystal introduced at the very beginning of this journey has, by now, grown considerably from where it began, its edges sharper, its structure more complete, built up patiently across the many hours this story has followed since first introducing it. Tonight, or perhaps some night not long from now, a shift in the water level, a gentle stirring of wind across the pool's surface will finally dislodge it from the place where it formed, carrying it toward the shallow edge, where the last of the pool's water evaporates and leaves it, finally, exposed to open air. From there, the wind takes over entirely. A gust catching the loose salt and mineral crust along the pool's margin lifts the crystal along with countless others, carrying it out across the wider flat in a fine, drifting cloud, indistinguishable at that point from any other grain of mineral dust swept up in the same gust. It will travel some distance, perhaps only a few meters, perhaps considerably further, before settling again onto the vast, pale surface of the salt flat, one tiny addition among billions already resting there, each one carrying its own small, unrecorded history of formation within some particular pool at some particular moment, shaped by conditions found nowhere else on the planet in quite this same combination. There's something worth holding on to in this small, quiet ending, a single crystal's journey from formation to dispersal mirroring in miniature, everything this landscape has demonstrated across the whole of this journey. Nothing here happens quickly. Nothing here happens carelessly. Every color, every mineral terrace, every pulse of molten rock rising within Ail's crater, every layer of salt laid down across 1,000,000 years of flooding and evaporation, and now, finally, this single crystal, carried by wind across ground, shaped by the same deep forces responsible for everything else explored tonight, all of it traces back to the same patient, ongoing processes, chemistry, and geology working themselves out according to rules far older than anything resembling human observation or human time. This is a landscape still being made, even now, even as the night settles fully across it and the last of the day's heat finally drains away into a sky filled with more stars than most people will ever see in one place across their entire lives. The crust beneath continues its slow separation. The lava lake continues its quiet churn. The salt continues its patient accumulation, layer upon layer, exactly as it has for longer than any single measurement of time could comfortably describe. Somewhere beneath the visible surface of all this stillness, 3 plates continue their imperceptible drift apart, exactly as they will continue tomorrow, and the day after, and across every day still to come, long after this particular night has ended. The extremophiles within the acid pools continue their own quiet persistence, dividing, adapting, surviving within water that would destroy almost anything else. The salt caravans, resting now somewhere along the route toward the highlands, will rise again before dawn to continue their journey, carrying with them blocks cut from ground that has been forming, patiently, for millions of years before anyone thought to give this depression a name at all. Somewhere out on the flat, in the deep quiet of this particular night, that one small crystal now rests among countless others, indistinguishable to any observer, and yet carrying within its structure the entire story this journey has followed. 3 plates pulling slowly apart, heat rising from deep within the earth, water finding whatever path it can toward the surface before losing itself to evaporation, leaving behind only this, a landscape more colorful, more extreme, and more quietly remarkable than almost anywhere else this planet has to offer. The Danakil Depression continues, tonight, exactly as it has for millions of years already, sinking, slowly, beneath 3 plates still pulling apart, glowing, faintly, within a lava lake open to the sky, crystallizing, patiently, mineral by mineral, across a salt flat holding the memory of ancient seas, waiting, quietly, for an ocean that has not yet arrived. Good night. Sleep well.